Howdy y'all, it's the Diabolic V-Tutor, and we're here just to continue on with graphing of the trigonometric functions, specifically sine, cosine, and tangent, and then hopefully get to the reciprocal trig functions like secant, what was the other one? Cosecant, and then cotangent. So let us begin straight to the graphing. Okay, so last time we talked about just the three main trig functions, sine, cosine, and tangent. So let's just do a little bit of review. So let's say we start off with a cosine. We have cosine of, don't forget this number in front of the x. So we do have a period change, and then we're going to do like a minus pi right here or whatever. That's a pi, by the way. And then we have like a amplitude change of 3. We have a minus, and then we have a 1. So this is going to be a vertical shift. We'll call this f of x. So just maximizing on the number of transformations we got for this particular function. It's not too bad. It's just a bunch of tiny rules. But just to reiterate from before, a lot of the rules are recurring. So thankfully, not total mess of things to memorize. But there are some things that are unique to the sine, cosines, and then also to the tangents. Alright, so first things first. How do we get started? Let's draw the x-axis. We've got the old y-axis. And then we'll acknowledge a few things. Number one, this one is a modified x, so we should factor out the 2 from those terms. Both terms to get the true shift, because this minus pi is not the true shift. So please group them, factor out the 2. We're going to get 2 times x minus pi over 2. We'll copy paste the rest of those. We'll keep the minus in the front, and then we can put the plus 1 off to the right hand side. Just to make it clear that it's explicitly a translation upwards of 1 space. But you don't have to do that. Alright. So, again, when we're finding the true period, we have to take into account there's just an x, but then it's modified by this times 2. So we set the times 2x is equal to the typical period for the unmodified cosine or sine function. It's just going to be 2 pi. 2 pi is the magic number because it's full circle, it's 360 degrees, and there's a certain periodicity to our trig functions. So let's divide both sides by 2. X is equal to just pi. So that's going to be the length of the period. And to begin, I just like to put the 4 hash marks as usual. So here's x-axis. Let's put 1, 2, and then actually I should probably go for some proper scaling, consistent scaling, I should say. 2 hash marks. We got 3 hash marks. Whoops. We got 3 hash marks, and then we got 4 hash marks. No, we just copied this one. And now we'll go and proceed in the other direction. Actually, that's more than what we need. Okay, and then we got to put the hash marks on the y-axis. So 1. And just going for some semblance of consistency. Obviously, it's better if we have like a pre-created graph, of course. I think I'm just going to copy this one and then graph subsequent graphs on this one right here. So, gotta make this one pretty good. I'm going to take this part right here. I'm just being a little picky with the graphing. Because if we don't, then the shifting rules are going to be a little wonky. Alright, that's good enough. And I'll just copy one more of these. I don't know why these hash marks have little hooks on them. It looks a little sinister. Okay, so what I'm going to do is I'm going to take this entire graph, I'm going to copy paste it and put it on a different layer. And it should be good to go. Alright, so again, the period is going to be, the period length is going to be pi. So starting from the 0, going to the 4th hash mark, I'm going to label that as pi, because that's my, I just like this methodology. You can use whatever method you wish. So half of that is going to be pi over 2, and then half of that is going to be pi over 4. This one plus this one gives us this one, which is 3 pi over 4. So 4 hash marks are good to go. We have an amplitude change of 3. And then we have a reflection, and then we have a shift upwards of 1 space. So I should probably put one more. Let's do that one right there. Alright, so that's kind of the odd one out. That's okay. Alright, so getting to actually graphing the situation. So what have we accounted for so far? We've accounted for the period change, and then we'll take care of the amplitude with the base cosine function, and then up to the 2x. So if we were to just graph this cosine, cosine begins on the amplitude number, which is 3. So instead of being 1, it begins at 3. Amplitude change, and then it's going to go concave down just by typical cosine movements. So right here, we talked about this last stream, hits the 0 and then goes 1 space over to the next hash mark, but hits the minimum, so -3, and then transitions to concave up as we move across to the next hash mark, hits the 0, and then when we move to the final hash mark of the full period, it goes back to concave down. Let me try to get this accurately, right there, and concave down up to there. So that's taking care of the cosine function, taking care of the period change, and then we've taken care of the amplitude change. Now we just need to account for the reflection. I'm going to go to a different layer. So all our positives, all our maximums become the minimums, and then all the minimums flip over to become the maximum because of the reflection. So this is concave. That's concave down, so it reflects into concave up. The nodes remain the same. Nodes remain the same. What used to be concave up now becomes concave down, like so. I can do this accurately. Alright. Well, it is what it is. It's the mouse after all. And then we'll do concave up right here. So that is looking gorgeous, and then we will delete the underlying orange one. We'll keep the red one. So now we've accounted for the reflection. So all of this has been accounted for. We just need to take care of the true shift pi over 2 space to the right and then 1 space upwards. So we're going to take this one. We're just going to copy this motif. The minimum will meet up with the minimum, and then all the other points should line up with the hash marks appropriately. Now I'll just delete the excess if necessary. Alright, so that's looking pretty gorgeous, and then we're going to do our shifts as well. So again, pi over 2 shift to the right. Oh, I should have defined these axes. Whoops. But just to reiterate, the first 4 hash marks, my strat, I always like to make it to the period length. So first 4 hash marks. Oh, because I deleted it. That's what happened. Yeah, so I actually did put these already. It's pi over 2. So pi over 2 is going to be 2 hash mark movements, which is why I like labeling these things. is going to be 3 pi over 4. Alright. So going back to the red layer, we are talking about the graph now. We're going to shift all the anchor points 2 hash mark spaces to the right. So the nodes ones are the easiest ones to keep track of at the moment, so I'm going to drag those over. So that's going to be 1 hash mark over and then 2 hash marks over. Well, then we should be good to go. I'm going to, whoops. I'm going to take this part right here, I'm going to copy paste it onto the other side. Just to beautify the graph. So we've accounted for the horizontal shift, now we just need the vertical shift. 1 space upwards. And that's not going to be too bad. So I'm going to take that maximum that's on the y-axis and we'll drag it upwards 1 space. And then we're good to go. Of course, if we were asked to label a few things, we have to make note that there's going to be domain. The domain is going to be all real numbers. So for any trig function, actually no, not any trig function, just for the sine and cosine, the domain is all real numbers. And then the range is a little funny. We talked about it a little bit last time. But the cosine function or the tangent function, the cosine function or the sine function themselves always hover between 2 values, -1 and +1, because, make note again, that the opposite or the adjacent lengths will never be greater than the hypotenuse length. So the most you can get from those functions is going to be 1 or -1. Or 1, or the lowest is going to be -1. It's this modifier that will adjust the range itself. So again, typically this thing right here, or always, these functions always hover between -1 and 1. So if we assume that this function returns the maximum value of, outputs the maximum value of 1, then it gets modified by this -3. So it becomes 1 times -3, and then we have a 1 minus 3, which is going to be -2. So that's the lowest possible value that we can get out of this function. And then of course, what's the greatest value? Well, opposite land. So if we input a negative in this situation, if we imagine that the lowest output we can get from this function is -1, that -1 will be multiplied to this -3 to get -4. I'm sorry, +3. And then +3 plus 1 is +4. So thus, our x value should always hover between, our y value should always hover between -2 and +4 inclusive. So that's going to be the range. I'm using the bracket notation because I prefer this one. So if you want to be fancy smancy, you can do something like this. X and y such that y is greater than or equal to -2 or less than or equal to 4. This is, I think, more robust, but this one's adequate for my purposes. And then visually you can see that this is consistent. So we have a ceiling at 4. That is indeed 1, 2, 3, 4. Yep. And then we have a minimum value of -2. Count spaces, 1, 2. It's visually consistent, so that one should be good. This one's always good. And this is the period. We should start labeling these things. That's going to be the period. Again, from peak to peak, that's 4 hash marks, which is labeled as pi. So everything looks pretty consistent. And just for paranoia, we're going to just check one point, never check the nodes. Rather check the minimums or check the maximums. This is probably the easiest one to check. That point is going to be 0, 4. So if we input 0, that becomes 0. 0 minus pi is -pi. Cosine of -pi is -1. -1 times -3 is +3. +3 plus 1 is 4 indeed. So this point is consistent and this graph should be good. And if we just want to beautify this one, we can truncate it, cut it off just a little bit, if we so choose. And then it could look something like this. And there we have it, the graph of this one. So not too bad. We've seen worse things before, of course. So that's an example of the cosine one. Let's go to the tangent function, of course. So we have tangent of we're going to do pi over 4. That's not the best number. And then we're going to minus a 2x. And then we're going to have a goofy coefficient of 2/3 just for fun. And then we're going to have a plus 3. So absolutely wonderful. We're going to call this g of x. So make note of the transformations. We do have a reflection. We do have a period change. We do have a... this thing in conjunction with this one will give us the true horizontal shift. And then we do have an amplitude change. And then we have a shift upwards of 3 spaces. So let's deal with this nonsense first. Let's factor out the -2 from those two terms to get the true shift. So we have a -2 times x, and then we have a minus pi over 8. So thus, pi over 8 is the true shift, pi over 8 spaces to the right. We'll copy paste the rest of this nonsense. So we're doing the tangent function, which has vertical asymptote issues. And then we have a plus 3. Alright. So let's make note of the period. So typical period for a tangent function, that's going to be from one vertical asymptote to the nearest vertical asymptote, either to the left or to the right. We don't care. We just care about the spacing. And the spacing for the typical period spacing for a tangent function is just pi. And we discussed that last time again, because tangent is ultimately a ratio between sine and cosine, right? So since the modified number is like a -2x, I'm just going to put 2x just for this example. So if you have sine of 2x over cosine of 2x, that is ultimately what we can use to think about tangent of 2x. So we make note that the bottom portion can become 0. So whenever we get 0 on the bottom, that's a vertical asymptote. So how do we get 0 from the bottom? We're just going to take this one and we're going to force it to be equal to the inner quadrant angle in which the adjacent is 0. So take that. We're going to take the 2x. We're going to force it to be equal to. It's going to be the one that points upwards. That's pi over 2. So force this to be pi over 2. But that just gives us one angle in which cosine is 0. Let's get all of them. So if we add, for every increment of pi that we add or subtract, it'll take us to a coterminal angle. So we're going to put plus pi k, where k is an integer. K is an element of integers. Alright. So that's that nonsense. Solving for x, therefore, x is equal to pi over 4 plus every increment of pi over 2, plus or minus. So there it is. So this is basically how we travel from one vertical asymptote to the next. So if we default to k is equal to 0, then we get our first clear vertical asymptote, which is pi over 4. So this one is going to help us out for the initial graphing. So there's one of them. I like to get the -1 as well. So if k is equal to -1, we're going to subtract that from this one, thereby getting -pi over 4. Let me double check the math is correct. Minus, yeah. So those are the ones that I like to plant initially onto my graph. You can use whichever one you wish. But let's make note of a few things. So this one does have domain issues, which is again expressed with this particular situation with x values. So these ones will get us to all the vertical asymptotes, which means that x cannot be these values. So our domain for this particular function, x can't be pi over 4 and every pi over 2 iteration subtracting from it or adding to it. So we'll just put this one right here. The ghost of old properties. Okay. K is an element of integers. Yes. For that one, and then the range, if you recall from the last time's graphing, the range is all real numbers. We'll talk about this more in detail when we actually get to the graphing. Alright, but for now, all of this nonsense, that's just to find the domain and range. And then we have the starting vertical asymptotes. There are infinite vertical asymptotes. Remember, it's every instance of this one right here, but these are the ones that I'm going to use for the graphing initially. So we're going to have hash marks, and the hash marks that I choose, I always like to choose 4 hash marks. This 1, 2, 3, 4. These 2, and then these 2 along with the x-axis. I like to use those ones. In particular, this one right here is going to be pi over 4. Why? Because that's the first instance of the vertical asymptote traveling from the origin, which is like where I like to start. But you don't have to start there. It's preferable in my opinion. So this one is going to be negative pi over 4. And then make sure to draw the vertical asymptotes. It's kind of crooked. Okay, and just for consistency, I'm going to copy that and paste that over to the, right there. So if we want to get to any subsequent vertical asymptotes, we just need to move over a total of 4 hash marks over from one vertical asymptote. So from this vertical asymptote, if we move 1, 2, 3, 4, and this is going to be the period length. Why? Because we determined it right here. So every pi over 2 increment, that's the movement. This is the starting, this is one of the starting vertical asymptotes, and this is how we travel to subsequent vertical asymptotes. So the length here is traveling from one vertical asymptote to another one, so that's going to be pi over 2 spaces. So therefore, this one is going to be pi over 2 spaces as well. Oh, I copied the pi over 4. Whoops. Well, pretend that's not a pi over 4. You know what? I got to change it. So we're adding pi over 2. So that's going to be 3 pi over 4. There we go. And of course, we can go in the other direction to the leftwards. If we subtract them, 4 hash marks. Unfortunately, there's no hash mark right here. So from this one, it's going to be 1, 2, 3, and then 4. So this is going to be at negative 3 pi over 4. Well, this is kind of goofed up. That's okay. I'd have to delete this real quick. It's kind of bothersome. Oh, you know what? This is going to be bad. Okay, you know what? I shouldn't have put this on the same layer. Whoops. That's okay. We could fix this fairly easily. So what I'm going to do is I'm just going to copy this real quick. And then we'll delete what we currently have, and then we'll put the hash marks. Yeah. So this is going to be pi over 4. And then 1, 2, 3, 4. 3 pi over 4. Yeah. This is going to be negative pi over 4. And I'm going to copy paste the vertical asymptotes onto the layer upwards. Right, 1, 2, 3, 4, all right here. Alright, and now we can copy paste the vertical asymptotes. Again, the first one is at pi over 4. How do we know that? Because we did it mathematically right here. And then if we add pi over 2 spaces to the pi over 4, we get to the next vertical asymptote right there. Or if we subtract it from pi over 4, we get to this one right there. So counting spaces, it's every 4 spaces. So 1, 2, 3, 4. 1, 2, 3, 4. Those will be the vertical asymptotes prior to shift. So there they are. I guess I maybe jumped the gun a little bit right here. We should probably do the shifting now because everything is going to get shifted over. True space shift of pi over 8. So I shouldn't have been happy with this one. So we're going to add pi over 8. Yeah, this is done prematurely. That's okay. So we're going to add pi over 8 to each of those, to this one, and then we have to change this one as well, change the domain. So what do we have? We have pi over 4. It's going to get shifted pi over 8 spaces to the right. So what is this? This is going to be 2 pi over 8, so 3 pi over 8. So that one right here, let's change it. So that's the domain if we didn't have the horizontal shift. But we do have a horizontal shift, so it's going to be 3 pi over 8. And then this one remains the same because the shifting also shifts all the vertical asymptotes. So the spacing between the vertical asymptotes will be the same thing. So this one also gets changed. Yeah, that's going to be negative pi over 8. Wait, will it? Oh, we're adding to this one, I'm sorry. So this one becomes 3 pi over 8, and then this one becomes negative pi over 8. Yeah. Wonderful. Okay, well, now we gotta shift everything over. That's always gonna be fun. So everything gets shifted over pi over 8, which should be 1 hash mark, because this one right here, if you take half of pi over 4, that takes us to pi over 8, and that's going to be the shift. So we just need to move everything over by 1 hash mark space, and we should be good to go. So 1 hash mark space, and those are our new vertical asymptote locations. I think what have we accounted for at this point? We haven't done the tangent function quite yet, but we just acknowledge that the vertical asymptotes are present, so this one is accounted for. We still need to account for this one. We've accounted for the period change. We need to account for the reflection. We've accounted for the shift now. And then now we just need to do this one. So I did things kind of out of order than what I typically do, but I guess that's okay. All right, let's get to graphing. Let's graph the tangent function. It's going to be fairly straightforward. It's going to start off at 0. Well, it would have started at 0 prior to the shift, so I guess I should have shifted it afterwards, but I'm kind of mixed up today. Okay, so we're going to start off halfway between any of the two walls. So we can start halfway between here, which is going to be this. Start halfway between here, which is going to be this, or halfway between those two, which is right there, but I like to work on this one. So between wall number 1 and then wall number 2, halfway there is right there. So tangent of that one is going to report 0 because this is just shifted parental function. So you can imagine the origin would have been there prior to shift. Okay. And we do have a reflection, and then we do have an amplitude of 2/3. So let's deal with those. So number 1, instead of being 1 hash mark to the right and 1 hash mark up, and this is being 1, we instead have 1 hash mark, and then we're going to move down. But how far down do we move? 2/3, not a full 1. Alright, so if we count these increments as 1, then we need to hit 2/3 of that, negative 2/3, which is right here. So again, 1 hash mark to 2/3 movement. So in the other direction, if we move backwards, if we move to the left 1 full increment, it's going to take us to positive 2/3 because the reflection and amplitude working in tandem will take us right here. And then you just follow the trajectory. This is a vertical asymptote, so we will never ever cross it. What's going to happen is we're going to have some sort of projection and kind of creep along with it indefinitely, but never ever crossing the vertical asymptotes. Same thing right here. If we trust in this trajectory, we're going to do something like this. Make sure you creep along, but never ever cross vertical asymptotes. We can cross horizontal asymptotes locally, but never vertical asymptotes. Never ever. Whoops, I shouldn't bend it like that. Okay, that's the best I can do with this mouse. And then we're just going to beautify this one, connect it as nicely as possible. There it is. So we've just accounted for this 2/3 amplitude. We've accounted for this reflection. Because this one's going from up, down. The typical tangent function, if it's like tangent positive x, will be going from down upwards, like so. But we have a reflection on the outside. Sorry, on the inside. Oh, wait a minute. Did I goof up? This is a reflection on the inside, which reflects the inputs. Wait a minute. You know what? I think this is going to end up being wrong. That's okay. I think I always like to do the reflections prior to the shifts, so I should have done the reflection first. Yeah. Let me think about it. Let me think about it for a moment. So if the shift had been done first, let me do something real quick. Hold on. So I'm going to undo the shift. So the reflection has already happened. So just as a quick comment, so if we had tangent of just x, it would be something like this. And then if we have tangent of the negative, then all it does is it reflects our unshifted graph across the vertical, which in this case happens to be the y-axis. So it reflects into the orange. And then once we have orange, then we could just shift it. Okay, so it's correct. It's not too bad. Okay, that's good. Yeah, this is correct. And we could always test it afterwards. All right, so I was a little worried for a moment, but we should be good. So yeah, reflection is accounted for, the tangent function is accounted for, and the amplitude is accounted for. Period change is accounted for. Everything's done with that one. We've done the shift a while back, and now we just need to shift things upwards by 3 spaces. All right, so let me think of how I want to copy paste this. You know what? That's fine. I'm just going to redraw this. So we have a half. All you have to do is copy paste this across every single motif, between each and every single wall. Just copy this orange motif. So 1 space to the left, and then 2/3 spaces upwards because of the amplitude and the reflection. So it looks something like this. And then 1 space to the right, but then 2/3 space downwards because of amplitude and reflection. So I think I lucked out that the reflections are the same. Okay, and then here as well, because again, typical movement is 1 to 1 hash mark, but because we have amplitude change, it's just 2/3 and reflected. So something like that. 1 hash mark, 2/3 down. So there-ish. Brilliant. And then we're going to take this one and we're going to drag it upwards of 3 spaces because we have a vertical shift upwards of 3 spaces. So that's going to be 1, 2, and then 3. So we make note that this new point right there should still be at 2/3. Whoops. It should still be at 2/3. So maybe just raise it upwards a little bit more. Okay. So if we kept track of that, this one is still going to be 2/3. So it's going to be 0, 2/3 above the 3. This is hash mark 3. So it's 3 and 2/3. I don't like mixed numbers, so 3 times 3 is 9. 9 plus 2 is 11. So 11/3. And that's going to be this test point. We're going to use it just to see if this answer is reasonable. Let's see if it's reasonable. 11/3. So 11/3 times 2 gives us 22/3. Ooh, that sounds kind of bad. Something is awry, I think. Okay, well, that's... Oh, what am I saying? Whoops, I'm sorry. I'm plugging in 0. What am I doing? This is the y. So we're plugging in 0. So pi over 4 minus 0 is pi over 4. Tangent of pi over 4 is positive 1 times this one is 2/3, and then 2/3 plus 3 is exactly what we did to get this value right there. So we have good confidence that this answer is correct. Yeah. So thankfully we are good to go. We checked this singular point, so we should be good to go. And we make note that our vertical asymptote's correct. We have a, what's that? This is pi over 8 plus this one takes us to here. So that's 3 pi over 8. So that's going to be the lowest possible positive vertical asymptote. And then every increment of plus pi over 2 should be correct. Yeah. So there it is. That's the graph. Thankfully it worked out. Again, I thought I screwed up the reflection, but it was actually okay. And we could truncate our graph however we wish. Maybe cut it off like right here. Okay. So that's going to be good to go. I'm going to put one more of these right here. So we've graphed the cosine, we've graphed the, what is it? The tangent, and then the sine is pretty much the same thing as going to be the cosine, follows the exact same rules. So instead, we're going to just jump to graphing the reciprocal functions. So specifically secant and the likes. So let's talk about those for a moment. And I think this is the first time I'm on stream I've talked about these, but for the most part, we've just focused on the 3 basic ones. We have sine, cosine, and tangent. So classic SOHCAHTOA for these ones, right there. But we can actually transform those ones. What's the transformation? So we have something called the cosecant, the secant, and then the cotangent. And that basically arises when we just take the reciprocal of these things right there. So if we do 1 over sine of x, that's going to give us cosecant. And then if we take the reciprocal of this one, 1 over cosine of x, that's going to give us secant. And if we take the reciprocal of that one, it's going to be cosine x over sine x. Because remember, tangent of x is just the ratio between sine of x to cosine of x. So this is this one. But if we take the reciprocal, that actually takes us to cotangent. And this is the one that's useful for memorization. So the cosine here becomes cotangent for this situation. But unfortunately, it doesn't work very well for these other ones. Like, why the heck does the sine one become the cosecant? And why does the cosine become the secant? Well, because everything is inverted. Let's just leave it at that. I don't have a good mnemonic for this one, honestly. It is what it is. So, unfortunately, cosecant is the reciprocal of sine, and then secant is the reciprocal of cosine x, not sine, unfortunately. This is the one that does make sense. The cosine's on top, and this is cotangent. So these are called the reciprocal trig functions. Is that how you spell this? Maybe. Reciprocal trig functions. So when we perform mathematical operations on these ones, it's honestly not that much more than what we've already been doing. You just flip the results. So for example, if we were to take the sine of this particular angle, for example, this is going to be the classic 1 to 2 to root 3. So taking sine of this angle right here, we call this one, if we call that one theta, then sine of theta is equal to opposite over hypotenuse, which is 1/2. But if you were to take cosecant of theta, that's just the reciprocal of this one. So instead of doing opposite over hypotenuse, we do hypotenuse over opposite. And that's just going to be good at 2. So this one, we can get ratios greater than 1. This one, we can never get ratios above 1 or below -1. And that's going to be the fun stuff, but we're not particularly concerned with the mechanics dealing with that just yet. We're just strictly doing the graphing for these ones now. And I'm going to show you it's going to be the exact same thing as what we already are familiar with. So let's take cosecant, for example. So suppose we are given cosecant. Let's do an easy one first. Let's just do x plus pi over 2 minus 1. And we're going to call this one h of x. In order to graph this cosecant, it's going to basically be a proxy of graphing sine, because this one is going to be the reciprocal of the sine function. So just pretend you're doing a sine function for now. So we're going to call this one sine of x plus pi over 2 close parentheses minus 1. So if we were to graph this, what would we do to graph it? So just to reiterate, we're graphing the sine function as a proxy for the cosecant one, but you're going to see how it differs afterwards. So starting from this one here, we're going to lay down the 4 hash marks. This is going to be standard period of up to 2 pi. So no period change. We do have a phase, we have a shift, but the period length itself is still going to be the standard 2 pi. So hash marks over, we're going to have 1, 2, 3, 4. I'm going to call this one 2 pi. That's going to be a full period. It's half of that. Half of that is pi over 2. This one plus this one is this one. 3 pi over 2. Alright. So we make note that the domain is all real numbers for the sine function, not the cosecant. Because this one has sine on the bottom of the fraction bar, which means you could potentially get 0, which means you can potentially get vertical asymptotes, which basically would mean we do have domain restrictions. But more on that later. Let's just focus on this one for now. So if we were to just graph this sine function, again, no phase change. We do have a shift though. So we start off at the origin. There's no amplitude change. So from this origin point, we're going to first hash mark over. We hit the maximum of 1. And then we move 1 space over. We go back to 0. And then we move 1 hash mark over. We get to the minimum, which is negative 1. And then once we hit the 4th hash mark, we reset. Oh, I missed this point right here. Okay. So concave down from there to there. Whoops. To the I can't do this. To there, we have concave down, and then for these 2 hash marks, subsequent hash marks, it's going to be concave up. It's going to be typical sine shenanigans. So we've taken into account that we're graphing the sine as a proxy. We've taken into account the period length. Now we just need to do shift and the shift. We need to shift pi over 2 spaces to the left because it's opposite land inside parenthetical, which is just 1 hash mark movement. So that's 1 hash mark movement. And then we're going to take the anchoring point, which is going to be this one right there, and we're going to move it 1 space down because we have a -1 vertical shift. So there we are. It looks pretty good. So if we were to take this, whoops, I'm going to botch this up, didn't I? I should do this on the next layer. Hold on, let me undo this one real quick. So I'm going to go to a different layer. Same thing as before. You hit the maximum, cross 0, hit the minimum, and then reset value right there. So we'll take this one, I'm going to copy paste it so we can duplicate it before we shift. Alright, that's good enough. And then we're going to move everything, again, we're repeating the shifts. I set this back to neutral position at 0, 0. So we need to move everything over pi over 2 spaces to the left. So that's 1 hash mark to the left. And then we have everything shift downwards because of the -1. So, whoops. If only this is better. Oh, that's okay. So make note of this anchoring point right there. So that would be the graph if we were just graphing this portion right here. But we're not graphing that. This is just a proxy for the graph of the cosecant. And here's how we graph the cosecant. We need to pay attention to the nodes in particular for the cosecant, because cosecant is ultimately just 1 over sine, right? So if we just look at 1 over sine, this is going to be one of those fractional functions, and unfortunately there's a function in the bottom, and this bottom portion can be equal to 0 at times. So the question is, when do we get 0 for this particular denominator? So all we need to do is just take that sine of x, and then we force it to be equal to 0. We make note that there's going to be interquadrant angles, so the easiest one is going to be 0. So x is equal to 0 radians. So that's going to be this collapsed triangle with a 0 opposite. But we make note that to get to subsequent sine functions that end up being 0, we can also get to this interquadrant angle. So that's going to be plus pi. And so for every iteration of pi we add or subtract, that takes us to the interquadrant angle that will result in a ratio of 0. So this one right here, we just need to put the k. So this is a familiar thing that we've already done. So k is an integer. K is in an element of integers. Alright. So these ones are where we create 0 on the bottom. So thus these are our domain restrictions. So x cannot be equal to 0 plus these things right here. So domain restrictions. We'll make note of range afterwards, because it is kind of weird for these reciprocal trig functions. So for now, we'll leave it blank. To be decided, to be acquired. Alright. So what are we pointing out? We're pointing out the fact that we can create 0. Where? Underneath the fraction bar, which results in failure of the function. So those are vertical asymptotes. So we do have vertical asymptotes at what locations? These locations. So since this is 0, I'm going to drop it and just keep pi k. Again, where k is some sort of integer. So for every pi that we come across, that's going to be result in a failure if we have an unshifted sine of x on the bottom, which is the unshifted cosecant. But because we have a shift of pi over 2, we do need to adjust all of these things right here. So that's not too bad though. Just shift it by, what do you call it? Pi over 2. So it's going to be, whoops. Oh my goodness. Pi over 2. So again, 0 is the default one if we were just working with cosecant of x. But we don't have cosecant of x. We have cosecant of x plus pi over 2. So that's going to be a shift. So the 0 will be negative pi over 2, which is right here. Negative pi over 2. I hope that's going to be clear. So this is going to be the true domain, and then the vertical asymptotes will be this one shifted over with a negative pi over 2. So let's take this one. Again, this one is for default parental function, but we do have a shift, and the shift is pi over 2. But remember, if it's in the parenthetical, we're dealing in opposite land, so don't put positive pi over 2, even though technically it would also be correct. But just to have some sort of consistency, just treat this as opposite land. So minus pi over 2. Again, pi over 2 in this situation would have been correct, but just to stay consistent, negative, which is right here. So we have a vertical asymptote right here, and you make note of something. It's actually piercing through the nodes of the sine function. You see that? This one right here. And that's very important. So this node right here, that's going to be the next vertical asymptote, because if we add one positive pi to this negative pi over 2, we get positive pi over 2. Which is right here. And that's going to keep happening. We're going to have to pierce through every single node. And the question is, why do we pierce through the nodes of the sine function? And that's because for the unshifted sine function, the nodes are where we get zeros. Right? That would make the bottom portion here 0, but we can't have zeros when we're doing division because that would create undefined situation. So that's why you could just use this shortcut. If you graph the proxy, the sine function proxy with the shifts and all, if you just draw the vertical asymptotes through each of these nodes, because again, that's where 0 would have resulted, unshifted, then we are going to be, what's I saying? Yeah, then we'll be hitting the vertical asymptotes. So shortcut is you just pierce the vertical asymptotes through each of the nodes, and the reason for that shortcut is because the nodes are where we would have gotten 0 for the sine function. And if we get 0 from the sine function, that creates 0 underneath the fraction for the cosecant function. So just to summarize what we've done so far, we treated this graphing of a cosecant function as graphing a sine function, so this is just the proxy. We pierce through the nodes to identify the vertical asymptotes for reasons we've already stated before. And then now here comes kind of the magical part of this whole situation. We now are going to graph the cosecant one. So here's how we do it. All you have to do is you hang out between the two walls, and then we're going to intersect at where this... We're going to intersect the minimums and the maximums of the sine function. So check this out. It's going to be something like this. So you swoop down, you hit that point, exact same point as the maximum for that particular sine function, and then we go back up. I'm not going to draw the arrows, but make note that there will be arrows right there. You can do the limit test just to verify that one. We might do a limit test, but let's avoid it for now. So that's going to be one motif for graphing the cosecant. And then for the other cosecant, we're going to hit this minimum. Whoops. If only I could do this correctly. Something like this, and then something like this. Again, technically arrows, but I think that looks ugly, so I'm not going to put the arrows. So this one right here, this is the maximum for the sine function proxy, but we're not graphing the proxy. We're going to use the proxy to graph. So make sure you hit that point, and then go back up. And never ever cross the vertical asymptotes. You can get close to it, but never ever cross. That minimum for the sine function is going to help us out with this one. We're going to swoop it up, go back down. Same thing right here. That's a maximum for the sine proxy, but we're not graphing the sine. So there it is. So all the blue stuff that we see, that's going to be the cosecant situation. Whoops. And then we should be good to go. We should delete everything in between. So at this point, the proxy has served its use. So we're going to start deleting the orange thing. I should have done this on a separate layer, but silly me. So I'm going to have to manually delete these. Absolutely wonderful times to be had. Almost there. Good enough, I would say. Oh, that's orangey. Hold on. Delete that, and we'll delete that. Okay, I think that's good enough. Okay. And then lo and behold, we now have the graph. Let's just frame this properly so it doesn't look like I just arbitrarily cut things off, which I guess technically this is what's going to happen anyway. Alright, so let's do like this. And then there we have it. That's going to be the graph of the cosecant of x plus pi over 2, close parentheses, minus 1. So we use the signage as a proxy to begin graphing the situation. This one we already know how to do with the shifting rules, so it would have shown up like this. And then we just use that one. We made note of where the nodes are located, because nodes are where you create 0 for the unshifted sine function. And then we use that in conjunction, in tandem with the graph of the sine proxy to graph the cosecant one. So you can kind of see it's, I don't want to say it's the opposite really, but it feels like it's the opposite of the orange graph, but not really. It is the inverse after all. Alright, so that's it for the cosecant one. Let us hit another one. We'll practice several more. Let's do a, what's a good one? Let's do secant. Yeah. So we're going to do a secant graph now. Secant of what? So we're going to have an amplitude change of 2. This is going to be something like 3x minus pi. Close the parenthetical, 1 minus 1. So we have a bunch of transformations to account for. And we're going to go back to f of x. Alright, so that's going to be it. Make note that we do have a period change. So I'm going to go ahead and group those together and factor out the 3 from those. So we're going to get 3 times x minus true shift, which is pi over 3. Close parentheses. This is a secant. Minus 1, and then 2 on the coefficient amplitude change. Oh, I guess I forgot to do the range. The range for the previous problem, I don't remember what it was. It was somewhere between, I don't remember. I'm going to have to maybe make note of that in the timestamps. Hopefully if I remember to do that. Yeah, but this is, you know what? Let me go back. It is what it is, unfortunately. Oh, okay, unfortunately I can't undo it anymore. Well, so much for that. Hopefully I'll remember to go over it for this one. Alright, so this is going to be the function. We have the true shift, and again, typically for a sine or cosine function. Well, before I mention that, I'm sorry. This is a secant, which is going to be the reciprocal function, the reciprocal of cosine. So it's 1 over cosine. So we're going to graph this one using the cosine proxy. So cosine, so we just pretend we're graphing cosine of copy paste. So we already know how to graph this one, and we're just going to find the period. So typical period for the sine or cosine is going to be 2 pi, but we don't have that. We have a 3. We have a modified x with a 3, so times 3. So thus the period is going to be 2 pi over 3, because we're 3 times as fast. So this one is going to be the period. Let's make note of that before I forget. So period length. Not where it begins, this is just the period length. The period length from peak to peak or trowel to trowel, or what I like to call reset value, is 2 pi over 3. Alright. Again, prior to shifts, this is just the lengths. Let's first determine, what else do we need to determine? I guess we could have left this one on like right here if we wish, but let me think about this. Is that the wisest thing to do? No, that's fine. We can just tack it on afterwards. Alright, so we do have a shift for the entire function. We'll keep track of that in a moment. But let's just get to graphing the cosine 3x. So again, this is going to be full period. So starting from the 0, 1, 2, 3, 4, we're going to hit 2 pi over 3. Half of this is pi over 3. Half of that is pi over 6. This one plus this one is going to be 3 pi over 6, which is pi over 2. Alright, so those are the hash marks. We do have an amplitude change of 2. So if we decide to graph the cosine proxy, it starts off at the maximum of 2. It's concave down. If we memorize the pattern, you don't have to memorize it. You can always verify it yourself. Then we're going to hit the minimum, transition to minimum for the next hash mark movement over. Starting from the minimum, go back to 0. From the 0, concave down, back up to the maximum. So here-ish. So there it is. I'm going to take this one and copy it prior to shift. Oh, I did the layer thing again, didn't I? Did I? Wait, what? Oh. Yeah, I think I did the layering thing. Whoops. Okay, well, I'm just going to undo this real quick and put it on the other layer. Hold on. Layer shenanigans. Alright, again, start off the maximum. Hit the 0. Hit the minimum. Go back to 0. Reset back to max. So this is going to be a full period length of 2 pi over 3, which happens to coincide with the 0 to 2 pi over 3. But this is unshifted. We do need to shift it. But I'm going to copy paste this one real quick. So I'll have an easier time shifting it. If you don't have the digital medium, if you don't have an advantage of this copy pasting shenanigans that I'm doing, that's just for convenience sake. Just keep track of the nodes and then keep track of the anchoring points. Alright, so we have that situation. Now we just need to do, what do we have so far? So for the cosine proxy, we've acknowledged that it's a cosine. We've done the amplitude. We've done the period change. We just need to just shift 1 and shift 2. So shift 1, we're going to be at plus pi over 3 spaces to the right. Yes. And we're going to keep track of the nodes because the nodes are particularly important because it's going to give us the vertical asymptotes for the secant. So make note, prior to shifts, where are these nodes? Those nodes result in y values that are 0, and we can't divide by 0. So that's why I'm pointing them out right now. Let me use red just to be consistent. So red will be the locations of where the vertical asymptotes will pierce through this proxy. Alright, so again, we're going to take this thing right here, make note of where the red things are. We're going to shift the red things over pi over 3 spaces to the right, which is 2 hash marks. So 1 and then 2. There they are. So at this point we can now get the domain restrictions because we're not graphing cosecant. We're not graphing cosine. We're graphing secant. So that's our period lengths, but we've shifted things by 2 spaces. So we should now have a, what am I saying? Well, we're going to identify where these red things have shifted to, right? So they've shifted to pi over 6. And then how do we get to the next one? It's half a period, which is just going to be half of this, which is plus pi over 3. So for every pi over 3 increment that we add, it will take us to a new vertical asymptote location, a new node, aka vertical asymptote. Alright. So again, we got these nodes graphically, but how do we do that? By actually just doing the mathematics. If you hate graphing, or maybe it's harder for you to identify things because you're doing this by hand. I did it digitally, so I had the advantage of being able to copy paste things, but we can still do it. So these are where the vertical asymptotes are located. And those ones I got straight from looking at the graph and doing shifting rules. But again, if we don't have that, no need to worry about it. We're just dealing with secant, which we acknowledge is just going to be 1 over cosine. Cosine of what? This entire nonsense. Or this entire nonsense. So we can actually use one of our older skills to get the vertical asymptotes for the situation. So again, this is a fraction, so we acknowledge that the bottom part cannot be 0, so we force it to be 0. So the question is, what does the inside the argument as a whole need to be in order to produce a 0 result from cosine? Well, cosine will get you 0 if you input the interquadrant angle number 1 or interquadrant angle number 2. But let's find this one first, because to get from this first one to the second one is just a matter of adding or subtracting iterations of pi. So first, we're just going to force this part to be equal to this one right here, which is going to be pi over 2. So you take the 3x minus pi and we force it to be equal to pi over 2. Because if this thing as a whole ends up being pi over 2, right here ends up being pi over 2, then cosine of that interquadrant angle, which is this one, has a 0 adjacent, which results in 0 as a ratio. So hence the reason for this particular mathematical setup, we're going to add pi to both sides. And then we're going to divide both sides by 3. So divide by 3, divide by 3. X is therefore equal to pi over 2. And this is going to be the first vertical asymptote that we can identify. How do we get to subsequent ones? Well, we should have kept the plus pi k. So let's go back just a little bit. So we should put plus pi k, because this one right here, with every iteration of pi we add or subtract, we will get to either this coterminal angle or this coterminal angle. So now that's the correct setup. With all coterminal angles accounted for, we're just going to add pi to both sides again. So same mathematics. And then divide both sides by 3. This one's also divided by 3. And thus do we get the vertical asymptote locations. And it should agree with what we found graphically. And then you see this one should agree with this one. And you're like, wait a minute, that doesn't look quite right. Like, why do we have a pi over 6 right there, and this is going to be a pi over 2? Well, this one is slightly, this is not the smallest positive angle we can get. This is the smallest positive one, because I checked it from the visual, right? But if you think about this, what if k is equal to -1? Then we're going to have pi over 2 plus negative pi over 3. So do the old cross multiplication. 3 minus 2 is 1. Common denominator is 6, and therefore we can get to the smallest possible positive value. So let us adjust this. So pi over 2 is correct, but pi over 6 is just slightly better in my opinion. So this will take us to all the vertical asymptotes, which again agrees with the graphical. This is just where one node is located. So if we add one more pi over 3, it takes us to this particular node. If we add another pi over 3, it'll take us to this other node. And again, we care about these nodes because those nodes create 0. And where you have 0 underneath the fraction bar, that's a vertical asymptote. Just to keep reiterating. Okay, but we're not totally done though. So all we did was we just confirmed that the nodes are where they're supposed to be mathematically and visually, graphically visually. We've done the shift, we've just finished doing the shift, and then now we need to do the shift upwards by 1 space. So let's take this entire thing and we'll move it upwards 1 space. Wait, did I do this right? 1 space. Alright. So there we go. And then now we're just going to do extensions of the nodes. So again, these are where all the vertical asymptotes will be located. We've already acknowledged it right here, mathematically. So now we just need to do it graphically. So again, nodes are particularly important. So 2 nodes, and then we got, let's not go overboard with the nodes. It's important this is misaligned. and then just to beautify the graph just a little bit. I'm going to take this part right here and just like transfer it elsewhere. I like it better right here. Not totally necessary, but just my preference. Depends on teacher how robust your graph needs to be. Alright, so there we are. And then of course we just need to finish off by putting the actual graph, because we're not graphing a cosine function. We're supposed to be graphing a secant, which is the reciprocal of that one, of that cosine. So again, here's how we do it. This is where the cosine was. We're using that as a proxy, but now we're going to put the real thing. So if this one's going to be concave down, we just need to do a concave up. So why does it behave like this? We can do the limit test to see why it's upwards. And then you could literally plug in a point right here. Whatever value this is, we can test that out. We're going to do that in a few moments. But why does it behave concave upwards? You can verify that with plug and chug. I'm just kind of lazy today. So there that one is, and then we have this one right here. We can try not to cross the graph. Try not to cross the vertical asymptotes ever. When you're sketching a graph. Mathematically, you'll never cross. Alright, that's probably the best I can do. And then I'm going to now wipe out the orange graph, because the orange graph is just a proxy. We don't need it. Well, at least we don't need it anymore. It served its purpose. So that's gone. We should probably keep the vertical asymptotes, honestly. And then we should be finished with the graph, but let me make sure I finally address the range issue. And then we're just going to verify a few points in the behaviors as well. Alright. Okay, we should probably test this point right here. That's going to be one test point. And that point is pi over 3, comma 3. Yes. So if we plug in pi over 3, then we should get equal to 3, right? So 3 times pi over 3 is pi, and then pi minus pi is 0, and then 1 over cosine of 0 is 1. 1 times... Wait, something seems wrong here. Uh-oh. Maybe something was shifted incorrectly. Let me think. So again, pi over 3 is the test point. Pi over 3 times 3 is pi. Pi minus pi is 0. And then... Oh, we didn't shift it downward by one space. Whoops. Did we shift it upwards or downwards? I think we shifted it. Hold on, let me see something. I think the shifting is incorrect. It's supposed to be downshift of 1. I think I upshifted it plus 1 by mistake. Yeah, I'm sorry. I think I did an upward shift. So this is a -1 shift. I think I did a +1 shift. Thank goodness for checks, right? So let's take this entire graph and we'll shift it downwards one space. 2 spaces to compensate. So it should have been like this prior to shift. Yeah, I shifted it upwards for some reason. I don't know why I shifted it upwards by 1. So this is where it's default. Prior to shifting upwards, it was right here. So we need to shift downwards one space. So right here. So which means this one, this test point should also get shifted from the default position downwards one space. So this is pi over 3, comma 1. And now the test should agree. So pi over 3 times 3 is pi. Pi minus pi is 0. Secant of 0 is 1. 2 times 1 is 1. And then 1 minus 1 gives us the fixed 1, which is going to be good. So that gives great confidence that this graph is correct. Let's try to beautify it just a little bit. Okay. And just let me do a few extensions. So the question is again, why do we have this particular motif? Well, we can just check it using... Let's verify it using some basic limits, right? So we're doing secant. And the consideration is what happens when we get closer and closer to the vertical asymptotes. And I'm just going to work with the smaller numbers. So the graph is already done. The graph is supposed to... Oops. So if we extend the graph just to beautify it, it should look something like this. Well, no, these portions are cut off. Okay, so again, we're just going to verify this real quick. Why does a graph look like this? Well, you just plug in pi over 2. Just kidding, you can't plug in pi over 2, because if you plug in pi over 2, what's going to happen? We're going to get 3 pi over 2, and if you subtract pi, we're going to get... what are we going to get? We're going to get negative pi over 2. Wait. I should be careful. Let me actually do this. I'm sorry, we get positive pi over 2, which creates 0 in the denominator, and then we can't divide by it, so it fails, right? So rather than plugging in pi over 2 directly, which will cause this function to fail, we're going to plug in something very close. But let's treat it as a cosine function real quick. So just to reiterate, the idea is if we try to put in the vertical asymptote pi over 2 directly into here, it will fail. So rather than plugging in pi over 2, we plug in something that's marginally less than, that's incrementally, infinitesimally very close to pi over 2, but is actually less than pi over 2. So we're plugging in something that's less than pi over 2, right? So if we do that, again, we're not plugging in pi over 2 fully. We're plugging in something very close to pi over 2. So as a result, we're going to get something very close to an interquadrant angle, very close to it, but not quite the interquadrant angle just yet. And something very interesting is going to happen. We're going to get, because we're very close to the interquadrant angle, we get an adjacent that's close to 0, but it's not quite 0. So if you take cosine of that particular angle, we're going to get almost 0. So this whole part right here, this whole part in the bottom, becomes close to 0. But it's not quite 0. In fact, it's still a positive 0 because we're still in quadrant number 1. So subsequently, since we're still in quadrant number 1, what ends up happening is this whole ratio becomes a huge number. Which I'll represent using this infinity sign, but it's still going to be positive. So 2 times a really huge positive number is going to explode upwards. It doesn't matter that we're subtracting 1. So this whole thing explodes upwards. So there it is. So that explains this behavior, and by explaining this one, we could also use that same explanation for this one. And also for this one, but we need to also address this one. Similarly, what's going to happen right here is going to be exploding upwards, much like how this one does. But let's talk about that in brief. So similar to the idea of plugging in a number that's very close to pi over 2, we're going to plug in a number that's very close to pi over 6. Or, yeah, we're going to plug in something very close to pi over 6, because again, if we plug in pi over 6 directly right here, we're going to get negative pi over 2 in the aftermath. And cosine of negative pi over 2 gives us 0, and we can't divide by 0. So we can't plug in pi over 6. We can plug in something conceptually very close, quote unquote, very close to pi over 6. but it's going to be a little bit bigger since we are on the right hand side of this vertical asymptote, right? So if we plug in something that's marginally larger than pi over 6, what happens? This whole thing here is going to get close to negative pi over 2. But it's going to be slightly bigger than pi over 2 because we plugged in something very close to pi over 6. So we're not quite at this interquadrant angle. We're like a little bit past it. A little bit behind it if we're considering it from a clockwise movement. So if we're still in quadrant 4, then cosine will give us a positive number. But this positive number is very close to 0. So what ends up happening is if we plug in something very close to pi over 6, but it's greater than pi over 6, this whole bottom portion here collapses very close to 0. It's not 0, it's close to 0. So therefore it still has a signage. It's going to be positive. So 1 over positive almost 0, we could represent it using positive infinity. Same situation as before. Positive infinity times 2 minus 1 is still a really huge friggin' number. So it's like this. And there we have it. Explaining that behavior. So by explaining those behaviors, we could also explain this downwards behaviors. It's just a matter of understanding some basic limits. You could also refer to the graph. Just imagine the reference triangles, and you can kind of mess around by rotating triangles. And here's what I mean. Remember back to the reference triangles? Recall that if we draw something right here, for example, this is going to be some sort of hypotenuse of length r. That one has a certain opposite relative to an adjacent. But if you take this one right here, and then you rotate it to right here, for example, then we are quote-unquote approaching pi over 2. But as we approach pi over 2 and maintaining the same hypotenuse length, what happens to these particular ratios? Make note that these ratios have changed. So the opposite has gotten larger at the expense of the adjacent. So if we're considering it from a cosine point of view, the cosine value is shrinking as we rotate this one closer and closer to pi over 2. In fact, the cosines begin to get smaller and smaller until it approaches 0, but never truly becomes 0, as long as we don't make it exactly pi over 2, because we can't. Otherwise this thing will become undefined. Alright, I hope that explains it. If you were curious about why the graph is in particular like this, rather than doing something goofy like crossing upwards and downwards, it all has to do with the trends. Pay attention to the triangle ratio trends. Again, if you start your cosine values at this particular angle here, if you keep making the angle, this particular angle approach pi over 2, you notice that the trend, the cosines are getting smaller and smaller. And if you're dividing by a smaller and smaller number, then the whole number grows bigger and bigger. So that's why we start off small, larger, ever larger, explosively large. Alright, let's not hark on that too much because we're not focusing on limits. That's probably more for towards the end of a typical pre-calc course and maybe the beginning of a calculus course. Calculus is what I mean. Alright, but we haven't touched on the tangent one, and that's probably going to be the last one for the day. Cotangent, I mean. So we have cotangent, but honestly, it's not tremendously difficult because this one is literally just a flipped version of the tangent function. And thankfully, this one has vertical asymptotes just like how this one has vertical asymptotes, except they're shifted over. So let me explain that for a moment. So recall that tangent of x is just equal to the ratio of sine of x over cosine of x. And then it's possible to make the bottom into 0, so we have to watch out for how do we make this bottom portion of the fraction into 0. And that just has to do with working with cosines. Cosines focus on these interquadrant angles, so it'll be plus pi k's. would take us to all the vertical asymptotes prior to any sort of horizontal shifts. But this one is just the flipped version of that one. So we have cosine of x over sine of x. So instead of forcing the cosine to be 0, we're forcing the sines to be 0. So this one relies on a different interquadrant angles instead of these ones. So the relevant interquadrant angles for sine x is the sideways ones, right? The sideways collapsed triangles, which is going to be 0 and pi. So as long as we plus pi k, we can get to all the relevant interquadrant angles for the sine x, which is how we create 0 on the bottom, which is how we find the vertical asymptotes for this one. Everything else is pretty much the same thing, honestly. So let's check that out real quick. Let's just graph the basic cotangent first. So this one we don't need to do the proxy. We could just jump straight to graphing the cotangent, because if we know how to graph this one, we just follow the same idea to graph this one. So there's no need to make a proxy like with sines or like with the secants or the cosecants. So, you know what, let's change this problem. Let's just change it to x minus pi over 2. Let's keep it simple. And then we'll have a minus, and then we'll have a 1 is equal to h of x. Alright, so that's what we're dealing with. And again, the first steps that I like to do, I just like to change this into a ratio of cosine and sine, because it makes it easier to identify the old vertical asymptotes. I should probably keep this one, yes. Alright, so that's essentially what we're dealing with. So opening move, we're going to try to find the vertical asymptotes first. So we're going to force the innards to be equal to what? Like we already mentioned before, this sideways interquadrant angle or this sideways one. So we're going to take the x minus pi over 2, and we force it to be equal to 0, which I'm not going to write anymore. You know what, let's keep it 0, and then 0 plus every increment of pi or minus every increment of pi. So that's the setup for the situation. Let's move that over real quick. Okay. And then moving forwards, we just need to solve for the x, so therefore just add the pi over 2 to both sides. And thus we get to all the increments where we can get the vertical asymptotes. This is already accounting for the shift with the minus pi over 2, minus pi over 2. So let's plant the first vertical asymptote at pi over 2, because we're making k is equal to 0. But let's define our hash marks first. So we're going to name this one, well, just because of this one right here, I'm going to name the second increment 1, 2, second hash mark. Name it as pi over 2. This is going to be pi over 4. And thus this is negative pi over 2. That's negative pi over 4. Looks good for now. And then we're going to start laying down the vertical asymptotes, because again, if k is equal to 0, then this is just pi over 2, which is the first vertical asymptote. And by first, I mean the smallest positive vertical asymptote after the shift. And of course, we can set k is equal to minus 1. So if it's minus 1, then the second vertical asymptote, the smallest sized negative, is going to be at negative pi over 2. I like to center things around the origin. So again, we've already accounted for the shift, so there's no need to worry about shifting shenanigans at this point, because it's already been taken care of. And then we can think about the graph itself. We're dealing with cotangent. So cotangent, we still have this particular point right here, thankfully, because again, if we plug in 0 into a generic tangent function, so let's look at tangent or cotangent, right? Wait, something seems wrong here. I have a feeling that something is supposed to be shifted over. That's okay. We'll do the test afterwards. So if we're... let me think. This is correct. Yeah, that's correct. And then because of the shift, everything shifts over. Yes. Yeah, I should have shown the untransformed one first, because I think the vertical asymptote would have been at 0. Okay, that's fine. So we're just working with this particular function. Let's not look at the tangent function. So this point belongs there. Why? Because if we take cosine of 0 over sine of 0, what happens? In this particular case, since everything is shifted over, it's actually okay. Normally this would be default to undefined, because we have this minus pi over 2. It's kind of quote-unquote saved from the situation, right? Yeah. Okay. So we're saved from the situation from the undefined denominator. I'm sorry, from the denominator resulting in 0. This part right here becomes cosine of an interquadrant angle, which is very familiar. And then the bottom one becomes sine of pi over 2. So this one is okay to do. It's referring to this one in particular. So it's going to be 1, but then the cosine of this one, it has no adjacent, so it's going to be 0. So hence, this point right here. This is actually a shifted point, because we've already taken into account the shifting rules, which I shouldn't have done at the moment, but it is what it is. And the graph is probably going to proceed in a very typical fashion. So is it going to be 1 to 1, or is it going to be 1 to -1 movement? Well, in this case, just verify it. Let's just plug in pi over 4 into our situation. So we're plugging in pi over 4 into this one exactly. So let's see what happens. So cosine of pi over 4 minus the shift, pi over 2. All over sine of pi over 4 minus pi over 2. So what do we get from that? We're going to get cosine of, this is times 2 times 2, times 2 times 2. So we're going to get cosine of negative pi over 4, and then the bottom and the sine of negative pi over 4. What happens in this shenanigans? Well, we're referring to which reference triangle? It's the pi over 4 in quadrant 4. That's adjacent 1, opposite is negative 1. So keep track of that. So therefore, we're actually going to get a -1 situation. Well, so not 1 to +1, it's 1 to -1, because we're dealing with cosine over sine, which means we're dealing with the cotangent, not this one. So this tangent function is the one where we typically go from typical pattern like this one, because tangent of pi over 4 is +1 if we have no amplitude change, but this one is the cosine over sine, so it's the flipped version. It's the reciprocal, so this whole thing is reciprocalized, if that's a word, like this. So follow the trajectory. So we could imagine it goes backwards 1 space and then upwards 1, because again we're dealing with the cotangent, not the tangent one. So that's if we're dealing with cosine over sine with a positive in front. So we've worked with this one, and we worked with this one, and we worked with the shift. Now we have a reflection and a shift upwards of 1 space. So wonderful, right? So again, if we disregard this reflection, our graph function would look like this. But now that we acknowledge this negative reflection, we need to reflect the whole thing across the horizontal. So it actually does end up looking like a tangent function in the end, which is just coincidental. And then we have an upward shift of +1. So we take this entire thing and move it up 1 space. And there it is. We should be good to go. I'm going to copy paste these ones right here, and then we're just going to be probably good to go. So let's put this 1, 2, 3, 4, 1, 2, 3, 4. So right here. I think I forgot the range for the other problem too. Ah, that's kind of sloppy of me. That's okay. Whoops. So we'll probably do another stream, being more methodical. I think this one I didn't really pre-plan it very well. But that's what happens. So we're supposed to get this. Let's not use this particular point to test. Let's use this point instead. So this point right here is specifically pi over 4 comma 2. So if we plug in pi over 4 into our original function, that's right here, then we should get 2 according to our graphical hypothesis. So pi over 4 minus pi over 2 is negative pi over 4. Cotangent of negative pi over 4, we already did that, but it's been erased. It's negative 1. 1 minus negative 1 is positive 2, so that is pretty nice confirmation that this test point is consistent. So therefore, this graph is probably good to go. And actually, I do have something to attend to, so I'm actually going to end it here. I don't think I did the best job today, but that's okay. It happens sometimes, but hopefully next time, next stream, maybe not tomorrow. Maybe tomorrow, I don't know, I haven't decided at this moment, but probably not tomorrow. Probably not the next day after, maybe the next day. But that'll be it for now. Again, not my best work, but we're going to be a little bit more methodical next time over. I'm just going to try to address the domain range consistently and in some sort of regular order rather than just kind of haphazardly jumping around, which is what I was doing today. So that's it for now. Hopefully I'll see you another time. Other than that, you have a good one.